particles are the building blocks of our universe. But how do scientists study and deepen our knowledge of this invisible world? There are 30,000 particle accelerators globally, yet only 70 of those are cyclic synchrotrons. These Goliaths of engineering are some of the most technically complex systems we've ever developed. And today, we infiltrate deep inside a semi-active Soviet nuclear facility to explore one that is in a deep state of preservation, and uncover the machines, electromagnets, and detectors that make it all possible. This is Yaris, the lost Soviet cyclic accelerator of particles. I found this location back in 2020, but due to global events, was unable to visit it. But now we were here, and I was joined by two trusted explorers to pull off this infiltration. There is almost no information about this location online, which made researching it almost impossible. But after some reconnaissance, we hatched our plan. The site was very active, staff moving between the buildings throughout the day and night. There was also on-site security and working CCTV within the territory.
We'll probably run along the fence, avoid the active buildings. We can dodge the security cameras and get through.
But like many post-Soviet countries, the ultimate security were the stray dogs who lived among the buildings. And soon, our plan was in place, and we were ready to venture into the night. Moving in complete silence, we traversed a steep cliff face. On one side, residential blocks, and the other, a 100-metre descent down to the valley floor. And the intermittent rain wasn't helping. In one section, we actually had to walk onto someone's balcony and crawl past an open window while they were still inside, something we really didn't want to do. This meant it took almost an hour before we were even near the territory, and now we were drenched and exhausted. Once we arrived, the terrain changed drastically. It was an apocalyptic Soviet wasteland, something straight out of Stalker. Abandoned construction projects, deep excavations, scrap metal, concrete and glass scattered everywhere.
If we see the ghost, we just go straight.
I think so.
It made our planned silent entry almost impossible. And as we avoided the cameras, the inevitable happened.
He's alone. Let's take the road.
We sent our resident animal lover forward to try to befriend the dog with some food, but sadly, this didn't work.
I think we just go quickly.
The amount of noise from this one dog was incredible, and security would have heard the commotion. Our time was running out.
We need to be silent.
Now for the most difficult part, the infiltration. There are no accessible windows, and all the doors had external padlocks which were checked on security rounds, but we already knew exactly where we needed to go. After squeezing through a labyrinth of confined spaces surrounded by asbestos, we had descended deep underground and were now in a cavern on top of the primary radiological shield. We had reached the heart of the facility, but we still needed to gain access to the accelerator itself.
The lock is closed. Change it.
Our first visit was much easier, with the padlock open for a quick entry, but our second visit found that lock replaced.
You know it?
No.
It was time to check all the other entry doors.
All locked.
We had one last resort, which involved crawling through the electrical cable passages to bypass the thick shielding and radiation doors.
It's possible.
Take out. Yep.
This led us to yet another radiation shielding door that was thankfully opened.
You think it's fine? The radioactivity? It's fine.
And then to the labyrinth of cable and ventilation tunnels beneath the accelerator. The scale of this object is incredible. Research at this facility was halted during the collapse of the Soviet Union and only briefly resumed in the early 2000s before being left to decay. And after the final maze, we had reached our goal, the heart of the synchrotron. And now it's time for a non-physicist to try to explain how a circular particle accelerator works in less time than it takes for us to walk around it. And hopefully it'll make more sense than my friend's attempt to visually represent it. Yeah, anyway, the subatomic particles originate in a source, such as an electron gun, for the linear accelerator, which is housed off to the side of the synchrotron. An interesting fact is that this linear section is aligned east to west to gain maximum energy from the Earth's rotation. The particle is then accelerated to 50 million electron volts by increasingly spaced cylindrical electrodes that use electromagnetic forces. The particles are also guided by focusing electromagnets that steer the particles within the tube. Once the particles have completed their initial acceleration, they enter the large circular accelerator known as a synchrotron. Eris has a diameter of 71 meters and a circumference of 223 meters. The particles would flow through the center of an aluminium tube that was under ultra-high vacuum so that it contained no air molecules or dust, which would otherwise prevent the particles from accelerating towards the speed of light. There are 24 resonators that generate the accelerating fields at 133 MHz, which increase the velocities of the particles. In just 8 to 9 microseconds, a single electron would reach energy levels of up to 6 billion electron volts. One of the complexities for a synchrotron is keeping the high-energy particles moving along the curved path. To achieve this, 48 blocks containing both horizontal and vertical beam-focusing electromagnets would exert calibrated forces to steer the particles within the narrow beam tube. Once the particles reached the desired energy levels, they exited the synchrotron at a tangent through one of the 5 primary beam lines. The beam lines pass through the massive 6-meter thick concrete biological shield, similar to what you would see in a nuclear power plant. These led directly into the experiment hall where additional particle manipulation, routing and alignment would occur before the particles would collide into various scientific experiments and detector equipment. The entire accelerator required a lot of support machinery to deliver the cooling, electrical power and frequency modulation in order to function, and these were all contained in the central machine hall. And all of these complex machines were controlled via an array of 1960s analog control systems from the building above. This accelerator had no modern computer interface, just gauges, chart recorders, switches, and valves. And now you know how it works. But we only made it halfway around the circle. That's how huge this place is. Sadly, the first section where we entered was extremely decayed due to the large volume of water that was entering the structure. They had placed large plastic sheets over the equipment in an attempt to protect the accelerator from further damage. We wandered around the ring, gazing at the mass of pipes, power cables, and electromagnetic coils. While this accelerator is impressive, CERN's Large Hadron Collider, which is the world's largest synchrotron, is 27 kilometers in circumference, or 125 times larger. The tube around the circular accelerator is actually elliptical and rather small, at just 6 centimeters by 2.4 centimeters. It was under a constant ultra-high vacuum. The massive yellow structures are called resonators and would switch electric fields from positive to negative at a frequency of 133 MHz. This switching is what creates the pull and push forces that accelerate the particles. They had large pipes which appeared to be for liquid cooling and some strange measuring probes and meters. The other major component is the electromagnets that surround the entire tube. These were responsible for guiding and focusing the particles around the ring, and judging by the size of the power cables, you can only imagine the forces being applied. And all this equipment required sub-millimeter precision to function. The radiological doors were also impressive and looked like something in a nuclear power plant or bomb shelter.
It's about 40 to 50 centimeters thick, and it's made of solid steel. It's absolutely gigantic. So the wall. So this is one of the chambers that would have allowed people the cyclotron. And yeah, just look at how thick this concrete is. It is absolutely massive, the amount of concrete used. And this is just to provide radiation shielding. It's got two solid doors, these two solid steel doors. Absolutely massive.
On the outside of the ring, we located the 5 beam lines through which particles exited the accelerator on their way into the experiment hall. A variety of beam focusing and manipulation magnets were installed here to prepare the particles for their next journey. These narrow tunnels in the primary biological shield allowed the vacuum tubes to pass through.
You can see here these massive magnets would control and direct where the beam was going. So one beam would come in and then they could split it out into multiple different segments. It looks like there's 3 different segments here. I can see 3 different pipes. So they would be able to use this gigantic electromagnet to basically route the particles to the required experiment area.
We crossed over the accelerator to reach another outer section, which appeared to be much cleaner, and that's because it sits next to the active linear accelerator. There were various cameras in this section, so we had to move carefully. The scientists had repurposed and upgraded the original 50 MeV linear accelerator, and it now had small-scale experiments set up in the main accelerator hall.
It's too small, bro. Is that what the camera?
Yes.
It's turned off, you think?
I don't think it's filming. I think they just use it during the experiments. I don't think it's CCTV.
We were careful not to disturb them, as they were all carefully calibrated.
Seems to be they're running something.
Yes.
Also.
Yeah.
It looks like brand new.
It is.
In the original configuration, this tube would have carried the generated subatomic particles and accelerated them to the initial velocity required for insertion into the main synchrotron. The Soviets have a reputation for questionable safety controls, but you'll be glad to know this one has an emergency shutdown button, an operational warning light, and this incredible phone.
No, it doesn't work.
Damn.
Sadly.
What a phone.
You might be wondering what would happen if you were hit by a particle beam, and amazingly, it has actually happened once in Russia during 1978. An error resulted in physicist Anatoly Borowski working in the experiment hall while an accelerator was operating. A beam of protons went through his skull, and after experiencing a white flash and receiving a localized dose of up to 3,000 sieverts, he simply continued his work and went home. Miraculously, he survived and continued to work as a physicist, suffering hearing loss, paralysis, and occasional seizures. And now that we've seen every part of the synchrotron, it's time to move on to the place where the real science happens, the experiment hall. And Anton was fully embracing the theme with his socks. Reaching this location required some creativity, as all the radiation doors had been welded closed this time. But thankfully, we made it inside. Despite being in a massive open room, it was challenging to navigate through all the concrete shielding blocks. We were dwarfed by these massive machines, and it looked like something out of a science fiction movie. Electromagnets taller than a human, particle sensors, beam lines, and guide magnets filled the space. It's in this hall where particles would collide with other materials, and the resulting particle collisions captured and recorded by complex sensor arrays, including magnetic spectrometers and a neutron hodoscope. A key focus for research with Yaris was the development and testing of new approaches to particle and radiation detection and sensing methodologies, which could then be used by other universities and nuclear facilities. As particles entered the experiment hall, their paths would be influenced by large focusing magnets. The scale of these machines and diameter of the copper windings gives you an idea of the forces these could generate while operating. Thankfully for us, they had no power, otherwise we couldn't get this close with our cameras. After continuing in the beamlines, these would arrive at the final stage of the experiment, where a particle or gamma ray collision would occur. This facility not only worked with electrons, but also high-energy gamma rays, which are produced by the electrons. Similar synchrotrons are used in the fields of chemical analysis, radiometry, and medical radioisotope production. The experiment hall contained 2 circular rings with beam-focusing magnet arrays mounted on massive rotating sleds, which could be moved depending on where the particles needed to be routed. All the equipment, despite natural decay, was in otherwise excellent condition, with no signs of theft or vandalism. It was surreal to wander through the maze of radiation shielding with all this Soviet equipment. It's now time for us to visit the machine hall. This zone contains all the electrical frequency generators, control panels, and power distribution systems. The sound of buzzing high-voltage electricity was still ever present. And the overhead cable runs were filled with thousands of cables. Soviet engineers had installed a massive rooftop power distribution structure where the electricity cables would enter inside the facility. Adjusted for inflation, it would have cost €6,000 in electricity per day to run this accelerator. Nearby, a set of dedicated transformers converted the main supply to the required voltages. The entire place was a Soviet time warp.
Because it's made in the USSR.
1963.
1963. It is 1963. What is more, this one it shows like how fast this goes to the ring, the water goes on the ring. It's written rings number 5, so everything that it was there, so probably here is supposed to be ring of water.
The other key function for this zone was to support pumping and circulation of cooling liquid. Massive tanks, filtration and pumping stations were scattered around and connected by a labyrinth of high-volume pipes. We also wanted to explore the upper levels of the superstructure where the research offices were located. This section was most certainly active, and motion sensors were a high risk for us. In one room, we found blueprints for the site. Most particle accelerators are built above ground, but the Soviets decided to build this one deep underground. This provided natural shielding from the radiation, but even so, the walls within this facility are incredibly thick, ranging from 3 to 6 meters. Accelerators can produce dangerous levels of ionizing radiation, but only when operational. This is why it was safe for us to enter without any protection. However, not all particles are successfully guided by electromagnets, and a quantity of them will collide with the beamline, machinery, and outer concrete walls with intense energy. These collisions can split atoms, which in turn become radioactive, often as short-lived isotopes. We also observed several radiation tags on different equipment.
Yeah, that looks like the experiment hall.
Damn. But this cycle is here, so it's supposed to be like
That's where we were before. Remember that section?
Yeah.
It's crazy.
Damn, it's good.
It's also the reason we found these personal dosimetry monitors near the main entrance, along with the machine to read the amounts of radiation received by the scientists.
Here is complex individual dosimeters. Yeah, so that's
individual. Yeah, got it.
So this one is all dosimeters.
Dosimeters.
USSR. So yeah, this is how to use it. Whoop. Looks like it.
It does.
Yeah. Tired. Very, very tired. exhausted to be on one place for so long.
What did you think, Akos?
Honestly, I cannot wait until we exit this place and we see the dog, because it's like it's been 2 hours barking at us. The dog knows that we are here, and it's gonna be very funny. I don't know what is going to happen, but it's gonna be amazing. Let's go.
Okay.
See ya.
And after 3 separate visits, we departed for the final time, leaving the accelerator behind in its concrete tomb. Sadly for us, even more dogs had arrived and awaited our exit, so we stashed the SD cards just in case security were waiting with them.
Do you think security will come?
I don't think so. I'm more worried about the dogs. It's interesting.
Exploring Yaros was a rare experience. The complexity of the infiltration, uniqueness of the object, combined with an unmatched Soviet atmosphere, is everything I look for in a location. But it was also sad to see this scientific giant decaying and rusting in silence, a shadow of its former self. Unfortunately, Yaros will never be operable without significant and costly renovations, and with technological advances, it would simply be easier to start over. Despite all this, the complex is clearly loved by the remaining scientists who continue to work there, and their dedication to advancing our knowledge of physics, despite a clear lack of funding and resources, is admirable. The future of this site is unclear, but renovation work in some surrounding buildings was underway. But for now, our exploration of this particle accelerator was completed, and we slipped back into the city, ready for the next adventure.
See you on that channel. Subscribe to others' channel.
You've got so much water on your hands.
I know.